logic behind line spectra. And as Julian said, that's a bit of an issue because it does look pretty darn random. Anything else? Julian?
Anything else significant about it?
Yeah.
I don't think so.
Yeah, no, there's something else. All right, Noah.
Future theories have to include this.
What do you mean fusion?
Future theories of the line spectrum has to
Say again? Future
theories must include the
future theories as to why the sun rises in the morning?
as to how line spectrum work.
No. All right.
Future atomic theories have to account for it.
Okay, any future model of the atom is going to have to account for why this equation works. Does it work for all elements, Nova?
No.
Okay, so any future model of the atom, the reason why this equation is also significant is going to have to account for why this model works so well for hydrogen, yet does not work for the other elements. Okay, so there's two reasons why this equation is important. One, it did affirm that, yeah, there is logic apparently, despite its initial appearance. There is logic or order behind line spectra. And two, any future model of the atom is going to have to account for why this thing works so darn well for hydrogen, yet it does not work for any of the other elements. Abby?
Are there equations out there for other elements?
Nope.
So how can we say that there's order behind line spectra if we only can explain one element?
It was more of an issue of the fact that they found one for hydrogen, the fact that they don't work for the others. Then it became a question of, do we want to actually go to the time and trouble to do it? In other words, was there anything to be gained here? You have to understand, we already knew the wavelengths for hydrogen's line spectra. We had determined those experimentally. So what Balmer was trying to do was to show that there was actually some kind of order here. The fact that he was able to come up with a mathematical formula that did that, really, that was the big thing he was after. The secondary significance to Rydberg's equation is not insignificant to us, but it wasn't what he was after. He was just trying to show that there was order or logic behind line spectra. The fact that he was able to come up with an equation that did that, that did it. If we did this for another element and came up with a different equation, that's only going to show that what we've already shown. There's logic or order behind line spectra. Okay? So now the question is, all right, well, we've shown that there is order or logic behind line spectra. Now we got another problem. This only works for hydrogen, though. It doesn't work for the other elements. So there may be other equations that we could come up with, but I mean, what's the point? Until we understand what's going on, there's no sense trying to go out and try to find an equation for every single element that's out there. A better solution would be to approach it from the standpoint that we don't even know what causes the line spectra to begin with. So it would make more sense, rather than trying to go ahead and come up with new equations, it would make more sense if we invested our time and energy to coming up with it, trying to explain, well, what's causing line spectra, and maybe if we can come up with a theory that can explain line spectra, then we might come up with a model of an atom that might actually explain why this works, and we might actually come up with a model that explains why it doesn't work for the other elements. You see what I'm saying? So it's a question of, the whole reason this equation was derived in the first place was to try to show there was order behind line spectra. We've done that. Balmer did that. So there's no real gain. You're not going to gain any additional insight by trying to find a new formula for a different element. That's not going to give you, it's not going to shed any more real light. Does that make sense?
Yeah.
To be fair, I don't know. They may have tried it anyway, and it may have just presented with itself with such a pain that they just realized that, you know, the cost of trying to do this versus what we're going to get out of it, let's put our time and energy elsewhere. Let's try to figure out how we can explain line spectra. Okay, and we'll come back, we'll circle back. So this is just an equation that we want to keep in mind so that when we look at a new model of the atom, it better be able to account for this. Other questions? All right, number 4, you had to calculate the wavelength in nanometers for a wave that corresponds to the second line of the Paschen series, and what is the frequency of that wave, showing your work. All right, Alexa, what did you come up with?
Not positive about this, but I had 1 over. Is that already wrong?
Yes.
Okay.
Okay.
Well, the number was.
Okay, well here, you take me through this, okay? So I want to go ahead and I want to find the wavelength in nanometers that corresponds to the second line of the Paschen series. The first thing I'm going to do is I'm going to plug into my Rybrid equation, 1 over lambda. So this is the first step to show me the formula. Second step, plug in the value. So I'm going to put in 1 over lambda is equal to 10.9.678 centimeters to the minus 1. Again, you don't have to show units, but I'm doing it because I think it's helpful to see what's going on. What do I put in place of n sub 1?
I had 1 over 3 squared.
3 squared, because it's the Paschen series.
1 over 5 squared.
And because we're dealing with the second line, that means it's 5. Everyone okay with those values that she's placed in there? Okay, at this point, because you've given me the formula, you plugged in the values, the only other thing I need now to see is a solution. Okay? Because traditionally this gives some people issues as far as the mathematics, I want to make sure that you guys know what you're doing. So I'm going to show additional steps, but you would not have to show all of the steps I'm about to show. It's up to you. So this is 1 over 9 minus 1 over 25. 1 over lambda is equal to 10.9.678 centimeters to the minus 1 over 0.111111 minus what, 0.04? Okay, solving that then 0.111111 minus 0.04. So this is going to be 1 over lambda is equal to 10.9.678 centimeters to minus 1. What? Question? Okay. Is equal to 0.071111. And then if we go ahead and multiply this, 1 over lambda is equal to, we multiply that by 10.9.678. We get an answer of 7,799.31. You want to keep this out to at least 5 or 6 sig figs because it's not our final answer. This is centimeters to the minus 1. Did you get that far?
I squared 4 instead of 3 for some reason on the bottom thing there, so all of my math was wrong.
Okay, all right. Did you get to this point?
Yes, I got it.
Did you stop at that point?
No, I did. In biology, we did like the sequence, so then I like tried to put it in nanometers.
What do I do? What do I do at this point?
Try to put it in. Oh no, you have to get it equal to lambda instead of.
So how do I do that? Because this is the part that usually gives people trouble.
I multiplied by lambda and then divided by the number.
Or another way of simply talking about it is just take the reciprocal of each side.
Okay.
You have to flip everything on its head. So lambda is equal to 1 over 7,799.31. And this becomes now centimeters.
Yes.
Okay, so if we go ahead and do that, we get lambda is equal to 1.282 times 10 to the negative 4th centimeters. We want to change that to nanometers, so 1.282 times 10 to the negative 4 centimeters. We know there's 100 centimeters to a meter. We know, bless you, 1 meter is 10 to the 9th nanometers. So we get an answer of 1,282 nanometers as our answer. Okay. Does that make sense? Why? Yeah.
Okay. Well, because you're moving the decimal place over, basically.
I don't mean does it make sense mathematically. I mean, does this answer make sense from a scientific standpoint? Oftentimes, you and I, when we're, as scientists, when we're working out and calculating a value, looking for a solution, we don't know. I mean, we take the numbers, we take what we got, and you work the numbers out, and you report what you find. And what you find, it might be like, well, I mean, that's what we got. But sometimes we have a general idea of what we got to do. For instance, if I asked you, said, I'm going to give you a length of string that's about 2.5 feet tall. I mean 2.5 feet long, okay? And I would like you to measure the length, using this 2.5 foot length of rope. I would like you to measure the length of this room, the width of this room. And I would like you to report back to me with how many feet the width of the room is, roughly. Okay, because you're gonna be limited to how much of a good of an answer you got since you're dealing with just a piece of rope that's 2.5 feet long. With me?
Yes.
If I were to go ahead and give this task to Abby, and she came back and reported to you that the room is roughly about 300 feet wide.
From this wall to this wall?
Yeah. See what I'm saying?
Yes.
I mean, you don't know what the answer is, but you, in this situation, we at least have an idea of what it should be around. So I'm asking you, does that answer make sense?
Yes, a nanometer is, go wait. That's, I'm saying yes, because.
Why?
Because the nanometer is so small that it's like, it's not like comprehensible to say 1,282, but when it's a nanometer, if you think how small that is,
So if I said the answer was 285 nanometers, that would be okay with you?
I don't know how to
You need to.
compartmentalize this.
You need to. Rami,
Yeah, I understand.
why?
The wavelength of red and violet are between 400 and 700.
Alexa?
This is,
Did you hear what he just said?
No.
Okay, so yeah, don't listen to other people, listen to
Okay.
what's being said. He just recited back to me what the range of wavelengths were for visible light. Can you recall what that is?
Oh, okay. It was 400 to 700
400 what?
nanometers.
Nanometers
To
to
700
700 nanometers. Could you remind me which side's which?
Violet's 400 and then red is 700.
Okay. So, does this make sense?
No,
Why not?
because, oh, wait. This is for passion. Sorry. No, because it's, oh yes, it does, because it's infrared and that's higher.
Infrared is a longer wavelength than 700, so we would expect it to be above. You guys understand? So this does actually make sense. It bears out. You would expect it to be somewhere in the infrared region. I asked you, what if I said the answer was 285 nanometers? No, because that would put it in the UV range, and it's not part of the Lyman series.
Okay.
Make sense?
Yes.
Questions at all? Michael?
When we use wavelength to measure like violet to red, is that the wavelength in air or the wavelength in vacuum?
It doesn't matter.
Is it close enough that?
We're just drawing a loose line in the sand, okay? It's not exactly 400 to 700. Those are just easy numbers to remember, okay? It might be 395.2. And the fact of the matter is, technically speaking, it's not the wavelength that's supposed to influence the color you see, it's the frequency. And now, based on what I told you yesterday, technically it's not frequency because there is no wave. It's photons. So that means that there's only a certain energy of photons that your eyes are capable of picking up and stimulating your optical nerve, right? Okay.
And then like at the borders between like microwaves and radio waves, is there like a significant like difference between the properties?
No, there's a overlap there. Yeah. Other questions? Okay. All right. In that case, going on to the next part of the question, which is, what's the frequency of this wave? And you had to show your work there. All right, well, we know what the wavelength is. To find the frequency, the only formula that allows us to get frequency, eta, is what? How do I get the frequency? Pardon me? You don't remember? Do you have your little worksheet on, not your worksheet, little review sheet, this one right here?
Oh, yeah.
Okay, I didn't put down the formulas, but you might want to list out, Ada, you might want to list out this formula on that sheet, just so, because it's something, all this stuff on the sheet you got to know. You have to have a committed memory. So you might want to put this one down. You might want to put down Planck's equation, E equals h nu. You also might want to put down C equals